Hello and good day, everyone. Welcome to this Lightbend webinar for April 22nd, 2020, titled Detecting Real-Time Financial Fraud with Cloudflow on Kubernetes. My name is Oliver White, Chief Storyteller and MC at Lightbend, and joining us today is my colleague and conference booth buddy, well, at least in the past, Gerard Maas. Gerard is a streaming systems expert, O'Reilly author, and Lightbend principal engineer. While I introduce today's webinar, which should take about 45 minutes, I would like to ask our audience a quick poll question. How long have you been using Kubernetes? I'm willing to bet that many of you have received a notification or email or text message of some sort from a bank or credit institution about some questionable purchase, or maybe more likely had an online purchase blocked because of suspected fraud. As digital commerce continues to thrive, financial fraud detection systems are evolving to provide more value and even predict fraudulent activity in real time. And as you can imagine, there's a lot going on behind the scenes. In fact, deploying a robust streaming data pipeline can be a very daunting task in general, but especially when your company's financial information is at risk. So to start, how do you ensure proper provisioning of resources? How do you preserve end-to-end application and data consistency? And how do you make all of this work in the cloud with Kubernetes and avoid YAML hell? We think that the answers to these questions and more is Cloudflow, our latest open source toolkit for simplifying the development, deployment, and operations of streaming data pipelines. And this is what Gerard is here to show us today: how to create a Kubernetes-based real-time fraud detection application for financial systems using Cloudflow. So if you're curious about what it actually takes to deploy, provision, and preserve end-to-end application consistency for your production systems, then this is a good webinar for you to see. We'll explore the Cloudflow API in action through a financial fraud detection app and move on to how to assemble your own application blueprint and run it locally before deploying it YAML-free to a Kubernetes cluster. The idea is that by the end of this talk, you'll have a pretty good idea of how to start working with Cloudflow for your own streaming data pipeline. All right, thank you for your answers. Today's webinar, as always, is being recorded and it will be shared with you next week. If you have questions for Gerard today, feel free to add them to the GoToWebinar control panel, and we'll see if we can get around to them in the Q&A part of today's session. If you are an existing subscriber with Lightbend, then you know that you can go directly to our customer portal and you can ask our expert engineers all of your technical questions, what-ifs, how-tos, and best practices. So that covers it from me. Let's all remember to wash our hands regularly and hand it over to Gerard. Gerard, thanks for joining us today.
Hi, Oliver. Thanks
Hello.
for a great introduction.
My pleasure. Are you wearing a face mask right now?
No, it doesn't go well with my mic.
That's true.
But I am staying inside, like all of us, and yeah, at least contributing that little piece of effort that we should all do to stay safe and get through these times of Corona crisis. I hope you all on the webinar are also staying safe, and that you and your families are doing well. Okay, let's get started with our webinar today. And as Oliver mentioned, we would like to talk about how to implement a Cloudflow-based model serving pipeline on Kubernetes. And we're going to use the financial fraud use case as an illustration on how to do that and how to come from a set of components to a end-to-end application running. First, let's go to the basics. What is fraud detection? It's a class of problem very similar to outlier detection and intrusion detection that wants to know which one of those elements, of those data elements, are not friendly to us, are meant to overpass or circumvent certain restrictions that we have put in our system. And in the past, typical techniques used to do that were based on rules engines and some business rules that our analysts were coming up with to determine whether or not a given transaction or a given network connection was an attempt to cause damage to the system at place. What we want to know is which one of those data points, data elements, does not comply with the rules of our system. And well, this is a very studied case in the data science world. And the data science process, what it wants to do is to transform that that world, or let's say that set of transactions, into something, into a formula. They want to approximate a formula that can tell us, well, if that transaction or that data point complies to this number of characteristics or features, then we have a certain probability that that transaction is fine, and we have then the inverse probability that the transaction will be fraudulent in nature. Coming from the whole set of data to this simplified scenario or simplified set of mathematical coefficients to a function is what the whole data science process is about. And it's, most of the time, it's a very batch-oriented, or let's say analytics-oriented process where the specialists look at the data, apply a well-known process to analyze it, to understand it, and to come up with some hypotheses that then are being tested to finally come to a representation that is, or what I'm trying to represent there in a very, let's say, high-level perspective on the right side of the screen. Then we want to use what we have learned from that process, and that process has been executed on data that we already knew, that we already had in our database, in our log files, etc. And what we want to do is that, let's say, transport that knowledge, get that knowledge that we acquired from analyzing offline data to our online application-based transaction analysis and transaction execution model. So here we have let's say, a high-level data coming in to the left side, and what we want to do is to compute it before, to then be able to say, well, some of those transactions, I am going to accept them. They are fine, and I route them, or I do something with them in the rest of my application. Some others, I will treat them in a separate path as a risk transaction that is potentially fraudulent. And most of the time, they will also have attached to them a risk factor if our model allows to compute for that. Today, and the key of our webinar today is how to go from one to the other, how to productize that output of the data science model into a real-time stream processing system that can use as functionality, use that newly acquired model into a real-time application. A real-time application that is then being deployed on Kubernetes, typically on a cloud provider, and that depends on a number of components to achieve its end-to-end functionality. The model there is not isolated in execution. It's probably replicated to many machines to achieve high throughput through parallelism. It's probably connected to a number of ingress machines that are accepting the data into the system. And then it's also probably connected to other systems in our infrastructure that are going to handle that transaction further down the line. So that is the context of the problem space that we're going to deal with today. That's what I call productizing data science. Having the output of the data science team, of those specialists that are studying the data, and then how can we bring the results, their outcomes, into a production pipeline that is deployed on the cloud. And doing so with reduced effort and lowering the complexity that most of the time goes attached to moving systems into the cloud, and especially on Kubernetes. There is where Cloudflow is going to give us a big difference, as I will explain today. And once we have understood what Cloudflow is and what it can do to us, or sorry, for us, it can prevent headaches, for example. That's what it can do to us. Then we're going to see how we can build a fraud detection model and run that model using Cloudflow. And let's say the first part will be a bit of background information, and the second part will be very hands-on oriented. I will go through pieces of code explaining you how the schema looks like, how the code looks like, how we deploy these, and at the end we're going to have an application running on the cloud. Or so I hope. So what is Cloudflow? Let's start by there. Well, Cloudflow is a software development toolkit. So it's a set of components that will enable you to develop, orchestrate, and operate distributed streaming applications on Kubernetes. And what do we mean with this development toolkit? Well, Cloudflow comes with two main packages, main pieces. One that I represent there with that laptop on the left side is something that you use on your computer. That's what you as developer are going to use day to day to develop applications and test them, get them validated. And then on the right side, we have the components that enable Kubernetes to understand Cloudflow applications as cloud native applications that are going to run on your Kubernetes cluster like they were just a pod or another deployment. On the client side, we offer an SDK, a software development toolkit composed of a Streamlit API. This is an abstraction that allows us to add information. It's actually metadata about how the inputs and the outputs are of a given stream processor, and attach that to a schema information. That's very important to preserve consistency between components. Then a blueprint is a way that we are going to compose all those elements together into an end-to-end application. This sandbox let us test everything locally before we have to package and Dockerize Amazon or Google Cloud. And then we also have a set of build extensions, extensions for our build tool that will allow us to remove a lot of the friction, a lot of the YAML creation that typically goes together with dealing with Kubernetes. Now that we know how the components look like and how they connect together, so well, we can also generate all the deployment that is required to have that running on Kubernetes and not give that experience or prevent you from having that headache actually. And at the end, we also have an extension for kubectl of kubectl that lets you govern the application that is actually running. So you can deploy it, but you can also change its runtime configuration and most of the typical day-to-day maintenance that you would like to do or operations that you would like to do on the application. On the Kubernetes side, we are using a principle that we call the operator federation, where we have or bring in our own operator, Cloudflow operator, but we rely on a number of open source components as well, like StreamC for Apache Kafka, and Akka Streams operator that we also provide, then operators for Apache Spark and Apache Flink. And the Cloudflow operator is the orchestrator of deploying the application, relying on existing functionality. So we actually building on the shoulders of giants to ensure that the whole composition it ends up or is at the end is a running application on your cluster. This federation also let us ensure that every component gets a specialized features and functionality with regards to the Kubernetes operations, like scaling up, like shutting them down, and configuring them. And they, of course, the two components work together through the kubectl Cloudflow plugin to enable you a very seamless experience from development to operations. I would like to say a few words about the streamlet, the concept of this new component model. As I mentioned, it's an abstraction of a streaming processor, and we support a number of those streaming processors. I will mention that in a minute. But the important element here is that we are describing how that processor, this processing component looks like. So it has inlets, it has outlets, and each inlet and outlet has a schema attached to that. That schema information let us determine when two streamlets can be connected together and validate that the graph of a streamlet is actually going to work or not. This is a typical pain that everybody suffers when you start deploying a number of connected components on a cluster. Well, they try to talk to each other. We use Kafka to exchange messages. But if you try to exchange a wrong message with another component, well, that component will fail or probably will not operate correctly. And the intention here is to enable you to evolve the application in a controlled way where you always know that your resulting application is going to be valid. And in terms of the executors for the streaming processing, so we support Akka streams, Apache Spark structure streaming, and Apache Flink. And that means that the logic that we're going to write there is logic written in the native, let's say, language of those components. The programming language we support is Java or Scala. But let's say the lingo that you're going to speak is going to be Spark structure streaming if you're using Apache Spark, and the same for Akka streams and for Flink. So you're going to directly use the API. It also means that you're going to reuse the knowledge that you already have about those backends. We're not introducing here a new streaming processing model. What we are introducing here is a way for you to think about applications and not only think about them and reason, but also provide you with the tool to connect them together and create consistent end-to-end applications that will run on your cluster. So what happens when you connect them all together? You come up with something like this. So in this case, we have an example of a application that is processing call records on a telco provider. And what you can see is that you have the ability to connect your streamlets to achieve, to implement the ideal scenario you have in mind that typically starts on a whiteboard, and you say, okay, those are the components of my application. That's how I would like to connect them together. And what we're providing you is means to go from the mental model directly to a structure that lets you implement that application. So you can merge different streams. Components can implement a given function. We follow here the microservice philosophy, where every component has a specialized function, and then it's also consuming a type or a kind of information and producing another one. And using the backends that are provided, you can also plug in the functionality that they offer. So for example, Spark and Flink have an extensive machine learning library and integrations with many others that can be exploited from that given context. And at the end, of course, you want to produce the resulting data to a downstream application. It could be a database, could be a dashboard, it could be another application, for example, that is consuming data in a streaming way. Let's use now, so that was Cloudflow. Cloudflow is fully open source, and you can find it on GitHub. I will share the URL with you at the end of the presentation. And now I'm taking a step back again and relocating where we are. So what I want to show you is how to go from that model realization, model creation to a production environment. And for that, this is a high-level data science process schema, and we are at the productization of the model side. So there we have passed already the whole creation and analysis of creation of the overall model, analysis of the data, validation, etc. And that process can be broken down as follows. We start from an existing data set that we would like to understand. So the first step is understanding that data. Then we start cleaning up and preparing the data, probably figuring out what kind of features we require from the data, probably also going back to the initial representation to see what we have there available to us to be able to come up with the model that we can use to feed to a training session. And so we would like to create a model and then provide known data to that model in order to create a trained model that contains information of that knowledge about that specific use case. We validate that, and again, there are like the feedback loops here, because at any point in time we can say, oh, this is, for example, if we do a validation and our model is not providing us with the right levels of confidence, then we can go back to the modeling part, or we can go back to the preparation part and add more features, etc., etc. And finally, we go to the deployment. So the deployment means that we're going to package that model that we created somehow, and that depends very much on the backend that you're using. Today, we're going to be using Spark, so we are going to pack up a Spark ML model. But if you're using TensorFlow, there are also a number of ways of packaging that model to be able to move it to a production environment. But it's not only about the model. We can also see that there is a parallel line from how the data flows into the system. So that transaction database, it didn't come to be from nothing. It came to be from collecting transactions over time. And those transactions are coming online to your system. So we have a data ingestion component there that is going to provide data into the system. That data injection, in our case, we are working with real-time stream. So this is a streaming data source that we're going to use to feed data into our system. The data preparation and feature engineering most of the time results in also the creation of those same features that we're using to train the model on the data that is coming in real time. So that same process that we did there for the data preparation needs to be translated into some filtering and cleaning up and enrichment that we are going to apply to the data, to the new data, to the real-time data as it comes in. And then finally, we need to import that model somehow into a runtime so that we have let's say, a management process and a management capability to load that model into the system, but also to replace that model when new versions become available. And at the end, of course, we want to propagate those results. We want, in our case of detecting fraud, what we want to do is to ensure that if one transaction has been marked as fraud, that we are going to, for example, stop the related payment that is attached to that transaction. This data science process, I see it as perpendicular as the data engineering part that is putting all the components together in a runtime environment that moves that knowledge, that model into production, but it's also going to deal with the online data, with the data that is being fed into the system at the moment that we want to apply that model. So in this case, we see the arrow there below is implementing our streaming pipeline, and we have broken down this into a number of elements. We have an ingress that is going to be the way we accept the data using a HTTP endpoint. Then that process of enrichment and features is going to be implemented using Akka streams. The whole data science part, we're going to summarize it into a notebook that is going to generate a model that we are going to then import into our Spark Streamlet for the scoring functionality. And finally, we are going to just show the data, or we will use a simple console output so we can explore the data quickly. And our use case in terms of implementation looks like this. So we have a Jupyter notebook running Spark. I have two versions. I have one in PySpark and one in Spark and Scala. I will use the Scala version today. That notebook creates a decision tree model. We are going to package the decision tree model into a container, and that will be our deliverable, let's say, from that process. And we are going to mount that in a persistent volume in Kubernetes so that we can access it from that runtime environment. And let's start with the notebook. I will go very quick over the notebook because that's really not the core of what we are doing today. I would like you to understand how that looks like, how the data science process has been summarized into a notebook that can be re-executed, it can be run. And we are going to put all these on the same repository of Cloudflow as an open source example. So you can go back there at a later, probably next week, where all this material will become available. Important to know, we will be using the Spark ML support for decision trees. The data set comes from a Kaggle competition. The process in this notebook has been inspired by a blog post by Databricks that you can read over there. So if you would like more details on the data science aspects of this work, I certainly recommend you to read that blog post. And from here, what we're doing is actually loading the data and understanding it. So going through those different steps that I mentioned before. So the data has a schema. The schema we need to have to parse the data correctly. It has a step and a type, amount, origin of the transaction, the old balance, the new balance, etc., etc. We can see a small sample of the data here, and there are some additional steps here, like we create a sample file so we can use it as an input for the job, for the application later on. And this is an important part I would like to highlight. So we are adding features to that data, and that a small piece of code will need to replicate on a real-time pipeline later on. So we are using the difference of the origin and the difference of the destination, two new features added to the data set that are going to play a role in the training stage, but they also need to be present in the later scoring stage. Then finally, we create a Spark ML pipeline. Again, I won't go into the details into that. We create a decision tree, train the decision tree, evaluate the results, and then finally, we are going to save that for the online scoring. And what you see here, we are saving the data, or we're saving the model, giving it a name, and putting it in a local file system. Well, that doesn't help us much, right? We need this data in the cloud. How do we do this? Well, we need to then maybe I'll do it like that. We need to package that model into something that Kubernetes can understand. And here's where we start with a bit of code. I hope you all can see my my terminal. And in that model directory, I have placed a build file that is going to package that model into a Docker container. And using that Docker container, we are going to run a job once it's already deployed on Kubernetes to copy the results that are contained in the Docker container into a persistent volume that has been pre-deployed already on Kubernetes. That's the way of the cloud. We don't have, let's say, access to the local file system, of course. The storage elements are shared, and you could also do the same on a storage service like Amazon. We are using here all Kubernetes native API so that you have let's say a Kubernetes-centric view on how an application is created. So we are there. Now we have deployed the model that we created with our notebook. And let's see what is the next step. Okay, let's go now into how our application looks like. And for that, we are going to see what the schema looks like. How do we represent the schema information, and how do we create an HTTP endpoint. To see this, I'm going to take you to my development environment. And here, again, I have a view of the data, of course, because I want to understand how the data looks like, in order to write down a schema for it. And that schema information we are providing using Avro. So we are encoding the schema information, creating a number of Avro schema representations. And here you again can find back the features of that data set. So we have a step, we have a type, we have the amount, the name of the origin, the balance, etc., plus an ID. And the important part is that we are not going only to represent the data that comes in, but the data as it looks like in every intermediate step. So we start with a transaction, and then after we have that transaction, we are going to go into an enrichment process. So we have an enrichment representation, we have an enrichment representation of that data that contains the enriched features as well. And once we have that enrichment part, we would like to give it to the fraud detection process, and that fraud detection process will give us a scored data. And that scored data will contain the results of the model, the prediction, is it fraud or not, and also metadata about the model that was used to score that the data point. All right. Once we are there, sorry, I forgot to show you the HTTP input. The HTTP input is really very simple, so you will be amazed at how easy it can be, because, well, we have implemented already some of the logic for you, so you don't have to write this very simple logic to create an HTTP endpoint that accepts post messages using the data type that we declared before. So we are using, as you see, we are using the schemas. We compile the schemas, and those compiled schemas we use to provide type information to every one of those steps. So the steps are also informed about how the data looks like, and we can use it to ensure that at the high level, using the schemas, everything connects together. But then at the implementation level, we can use type safety to ensure that whatever comes in has a given type, and whatever goes out has the type that we expect it to have. So in this case, there is only an output here, and that output is producing transactions, and this component will be parsing the data and will be ensuring that the output of it is a transaction before giving it to the pipeline. Okay. So we were here, we have seen how the schema looks like. We have seen the different aspects or how the schema is used to inform the shape of the data between the different components, between the streamlets. And now we are going to look into how that fraud detection component is implemented. Okay, let me go out of the view here, and that was the enrichment part. We just added 2 new features, as I mentioned while we were working on the notebook. Then we have the scorer. The scorer does 2 interesting things. Besides its main job of using a model and applying it to the data coming in, first it declares, well, this is the input. The input is a transaction that is enriched. The output is a transaction that is scored transaction. The shape, that is the metadata information that we add at the streamlet level. Okay, this is a component that has an inlet and it has 1 outlet. That's the way we express it in a very type-safe way. But then there are 2 elements here in addition to that are also provided by the Streamlit API. One is a configuration parameter. A configuration parameter says what is the what is the type of it and some default value, but also with some description Why is this important? Is because using these configuration parameters, we can update the pipeline while it's running. This is very different from the typical configuration files that we package with or build components already, and they are very difficult to update once they are in the runtime environment. In this case, we can update this configuration using the tooling, and that will affect the runtime. Will update that component with the new information, and we'll have the new version running. Why is it important? Is because our data scientists, they are not happy with the first model they come with, and they would like to deploy some new models. So here we have a default, but as they come up with new improved models, we would also like to update this at runtime. And then last but not least, we also have access to certain capabilities of Kubernetes. In this case, we are here declaring a volume mount that gives us access to a persistent volume mount on Kubernetes with a given name. And that given name will be bound to that models. And that way we can read from the volume mount and then load the model that we have written there. The rest, as you can see, is Spark structure streaming code. So besides this addition that we bring with the Streamlit API, well, once you enter into the writing your business logic, you are freed from all the overhead of having to set up connections to Kafka, having to set up Spark sessions, having to configure them, or even knowing how to configure them. We have gone into, let's say, very into lengths to ensure the operational aspects of the runtime. For example, provisioning as well a space where you're going to write your snapshots, where you're going to write your state, so that you can, at runtime, be sure that your application is going to work. And not only, giving you the space to write the business logic. So this is business logic plus batteries included for all the setting up that is required to have that running as an application or as a component of an application. And once we have those components developed, well, we need to connect them together. That is that arrow that we see there. And that connection happens by writing a small file, and we call it a blueprint. And that are streamlets present in my application. And this is an implementation of a streamlet. I give it a name. And once I have named my streamlets, this is also important because we will know the streamlets by name when they are running and not by the class that you implement. And we implement a very simple graph logic here. So the output of the ingress connects to the enrichment input. The output of the enrichment connects to the input of the scorer. The output of the scorer connects to the input of the transaction. Of course, this is a very linear setup, but you can have a connectivity of any complexity here. You can add new components there, or you can connect components together and form a directly cyclic graph of your liking in using that very small DSL. And at this point in time, we are all set. We have implemented our full end-to-end scenario. Let's see how that works in terms of building and running our application. I am now in the directory where my code is residing, and I'm going to use SBT to build the application. This is a building tool for Scala, which we have enriched with a number of plugins that let us, for example, verify that the whole pipeline works. And verify blueprint will load that blueprint that you just saw, and we'll check that the connections between the blueprints are working properly. And once we have this, let's say, check done, we are kind of we have a certainty that things are going to run. It's already, the data is okay, the code should be okay, everything compiles well. Then we have this feature, I find it very neat, where you can run the complete application locally on your computer before you try to run it on the cloud, before you package and load it and, I don't know, FTP it or whatever you do to have it at your cloud provider. And what it's doing is instantiating each one of those streamlets locally on a scaled down version of them, but providing you the inputs and the outputs that you would usually have on when you deploy this on the cloud. So there is an HTTP port available there, and there is an output where we can see the output of the complete application. And we can tail that output. Let's see, things looks quite okay. And I have a small script here to send data. And that send data takes a data set, a sample data set with, let me just stop it for a second because it has to be scrolling very fast for you. What we are doing is creating a post for data elements represented in JSON and compliant with the schema that we encoded earlier today. And you see we have the cash in amount, the balance, etc., etc. And what we should be seeing is that the data is being scored in my output. So let's start this again, and let's go back to my output, and we see there that our whole pipeline is working. And once we have seen it working locally, then chances are that things are going to work pretty well on my cluster. How do I get this application in the cluster then? We have a build and publish extension that will package the complete application. We create the Docker images that you require, and we'll tag those Docker images with information that we need to have it running on a target cluster. As I mentioned, the target cluster needs to be enabled with the Cloudflow operator or open source project. In the open source project, you find there a folder called installer, and under that installer, you find what you need to install the needed components on your Kubernetes cluster. We test everything on Google Cloud, and we have seen it working on Amazon and on Azure, but we don't maintain a build for those two. Okay. So we have now deployed that application on our target cluster, and I have a deployment. Sorry, let me just go to kubectl here, and I have a deploy script where we are going to take a token that we are going to use as the authentication for the Docker container. And once I do this, I start deploying, and you see that my persistent volume claim has been bound. And using the now we are going to use our plugin for kubectl, kubectl. We see that the application has been deployed there. It has the name of Sherlock pipeline, and I can ask about the status of the application. Is that all running properly? And it looks like everything is running. Maybe something is something has been restarting, terminating, and probably restarting because I had the previous version running already. So we see there, you can see the evolution of it as it gets deployed on the cluster. And I hope there we are. I think we are almost done, and we have an application up and running. Everything is ready. The status is running. And to be clear, we have an application using 1, 2, 3, 4, 5, 6 components. One of them is a Spark cluster using 1 driver and 2 executors, and then 3 deployments corresponding to the Akka streams elements that we have coded and then deployed on the cluster. How that looks like on our on our cloud provider here, that is GKE. You can see here that the application is up and running. And I guess the proof is in the pudding. We would like to see if this thing is working as we promised. And what we first need to do is we need to enable port forwarding from my machine to provide data to the ingress on the cloud. And then we can send data again. Send data is using the same port. And then it looks like we have something working. Now, let's see the output here. And we capture that, that output. So let's see, logs, this. Let's modify that last one. And we have transactions being scored on the cloud. All right, and we see this now it's being scored using Model 3. We are almost running out of time. We can reconfigure things, so we can say configure, and you can see that I had done some tests before, and we are going to reconfigure the application as it runs. Some of the components will be updated, and once that's done, the new data will be scored with the new model. Okay, I think we have seen how Cloudflow lets you create the application using, let me go back to my presentation. We are now at the, let's say, complete end-to-end scenario. We have seen that we could create a component that accepts the HTTP data. That was actually kind of simple and very easy to create. We can add enrichment features using any of the backends, and then we use a Spark structured streaming to apply an existing fraud detection model that we built using that notebook, and as a decision tree model using Spark ML. And finally, we produce data or the results to the console, but as you can imagine, you can integrate that with any element that you would like. All that communication goes through Kafka, so you could consume the data from Kafka directly and have your application connected to the fraud detection system in very little time. Just to finalize, what are the architectures that we envision using the system? So there are several and different ways of providing machine learning models on a streaming fashion. The one we have seen is the first one, where we have an embedded model. There is an external batch system that creates that model, provides it to the cloud in some way. We package it to Kubernetes using Docker containers, and we include it at runtime on that pipeline. The second way would be to have an external model service, for example, a TensorFlow serving that creates an external server that hosts the model, and we can use Akka streams functionality to access that model, for example, using gRPC or using REST. And finally, this is some work that one of our colleagues has been researching deeply. It's what we call managed streams, where the model is provided using a parallel stream and is joined with the data in the scorer function there. The advantage of that is that it provides you with a very low latency and a always-on system. What is the mission? Well, there are, I think, three main spears in that. Infuse the let's say, called the new line of smart applications in the enterprise. You can add your machine learning, but also help your machine learning and data science teams to productize their outputs, and mix the logic that we have with the streaming analytics and model serving and machine learning. And last, as I mentioned before, realizing that join of data science and data engineering, that the output of one is directly usable in a production environment. Getting started with Cloudflow, it's very simple. We have our open source project on GitHub under Lightbend Cloudflow, and we have a comprehensive set of documentation at cloudflow.io. So I hope to see you there. We have a getting started guide. I love to get you try it on your own. And if you have any questions on Cloudflow.io, you also get the channels that you can use to contact us through Gitter, to GitHub issues, or through Discuss. And I think that's what I had for you today, and I hope we have some questions online. Oliver, to you.
All right, thanks so much, Gerard. This was I know as much about Cloudflow as most more than most people, and I always learn something when I see you present. So this was great. We do have a handful of questions, so let's just jump right into it. Let's see. The first one, let me read it out to you. It's pretty well developed. So this gentleman has experience with Kafka streams, but he's not satisfied with the parallelism model because it leads to inefficiencies, which raises costs. So he's looking at Akka streams or Akka actors or Akka cluster, and the question is about horizontal scalability. So how does Akka streams in the case of Cloudflow, or rather Cloudflow using Akka streams support horizontal scalability? And if it doesn't do what we might want, is the actor model on Akka cluster a better choice here, and does that work with Cloudflow? So that's kind of a big one.
Yes. That's yes, indeed. Let's break that down into several pieces. First, how is a parallelism model? The Akka streams components, as they get deployed, they are deployed in what in Kubernetes is known as a deployment, and you can scale up your deployment. And I can actually very quickly show that to you. Oh, if I find the right screen there. So if we have our status here, we have, for example, this enrichment. The enrichment has been created using Akka streams, and we can then use Cloudflow scale Perlock pipeline, and then the component that we want to scale, and then give a scale factor. Once we do this, and we go back to our cloud view of things, or we can also do the status, you will see that we will start getting more enrichment elements, and we will have 5 in total now. So the scaling of Akka stream components is by scaling up the number of pods where they are running. That was the first, I think the first part of the question is configurable at runtime, and you can have, for example, a log analyzer or a load analyzer hooked into this and use the scale function to have some way of elastically scale your system. Then the other question was whether we can use Akka cluster. Well, there is a very recent pull request that adds an example how to do this from a Akka streams streamlet. So yes, that's completely possible, and the way that's done is again by using a Akka cluster deployment on Kubernetes and then accessing it from the Akka streams streamlet. I hope that answers the question, and if you would like to discuss more, please reach to us through Gitter or something. We can have a more in-depth discussion.
Great. So the bottom line is that you can achieve certain scalability with Kubernetes by itself, just by scaling as you showed us, but also Akka cluster will easily support scalability, as we all know.
Yes.
In the case that whatever that is doesn't work perfectly. Great. Thanks.
Exactly. And we can scale up or down, as you can see here.
Okay. The next question, can Cloudflow support time boxing with a guaranteed response within a certain time window? So I guess the use case would be, if X happens, we need to guarantee a response within 10 seconds, and if not, escalate, and so on.
Yeah. As I mentioned during the presentation, Cloudflow is implementing the orchestration of all the components. A window operation will be something that is implemented at the execution level, meaning that will be a function of a Spark structure streaming or Flink. And both Spark and Flink support window operations. I know very well Spark, and such use case will be rather easy to implement in Spark structure streaming. But I also know that Flink support for window-based aggregations is very strong. So any of the two will get you where you want to be. Will get that use case implemented. And again, it's not a function of Cloudflow per se supports the deployment of the Spark component of the Flink component that will be doing that window function for you.
So Cloudflow is kind of providing the glue and bringing everything together into a cohesive system so that you're not having functionality siloed off in a Flink platform or something like that.
Exactly. I think you could see Cloudflow as the microservice version of the streaming applications, in the sense that many times, oftentimes, organizations tend to pack every feature of their streaming applications into just one framework, into just one single job that does everything. I have helped in the past some companies to break those down. And what Cloudflow is doing is helping you break those down in a way that you still preserve your peace of mind, that all the components are coherent, that they can all communicate with each other, but then that you can have the best tool for the job to implement the different functionalities that you need for your application. So you could have Akka streams to implement the inputs and outputs. We have extensive support for HTTP, for Kafka, etc. You could have a Spark or Flink to implement, for example, that window function that one of our attendees was asking about.
Okay, great. There's a question about how what Cloudflow is providing gets translated in terms of Kafka topics. So in this case, there's a question about a DAG being described, and what does that look like in terms of Kafka topics, and are you able to kind of back into Kafka? I know that Cloudflow takes a lot of, well, basically puts Kafka in the background and allows you to focus on not messing around with Kafka provisioning and so on. But is there a way that the stuff we're doing with Cloudflow is kind of discoverable as Kafka topics in some way?
Yes. So we use a Kafka operator by Red Hat called Streamc, and we can call Streamc. Let me just. We can call Streamc to query Kafka applications. I think it is. Yeah. I don't know. I don't remember. I wanted to give an example, but yeah. Topics.
Are you Googling this right now?
No. I'm trying to.
Okay.
Sorry, you cannot. You don't see it. No. I'm not Googling it.
Oh, okay. I was gonna really laugh extra hard. That's what was going on.
Well, this is so you do, but I think we have that in the Cloudflow namespace. So there are the topics that we offer, and as you can see, their names are very stable. They are based on the Streamlit names that we have deployed. So there is an enrichment out, an ingress out, and a score out for the application we're working with today. Now, then again, this is a function of a open source component, so there is nothing closed in Cloudflow. You can get to everything, but you certainly need to know what you're doing with it. Just a word of warning, Cloudflow uses schemas to serialize and deserialize data that goes in and out from every of the topics. And so the data that is in the topic is warranted to follow and comply to that schema. But if you introduce data from the outside, then that schema information is not anymore warranted to be correct. And of course, we cannot guarantee that the components are going to be working properly. So that said, our recommended way of interacting with the data that has been flowing through Cloudflow is by producing it to a known topic that you develop, or sorry, that you deploy on Kafka. So you know where that data is going to, you know the shape of it, and you can actually have ownership over it. That would be my recommendation.
All right, great. I think we got time for one more. There's a question. Gerard, are you familiar with MLflow?
Yeah, I am somehow familiar with MLflow and with Kubeflow, being tools or tool chains to train models. Indeed, yeah.
Mm-hmm. So there's a question. If you're familiar with MLflow, then how does Cloudflow kind of fit in with that, or compare to it, with the specific look at tracking results of, as it's phrased here, every run. So I guess every run of a model, but in this case, it would be kind of a streaming continuous run. So maybe in terms of a batch style paradigm.
Yeah, Cloudflow and MLflow. Sorry, I wanted to say Kubeflow and MLflow being very similar projects. I see them as orthogonal to Cloudflow, and why? Because they implement the data science process. They implement what I mentioned earlier. They implement this. They go from the data through a set of known steps that are orchestrated by the tools. So in terms of MLflow or Kubeflow, you can design your data analytics, your data training pipeline, and have a validation step at the end that is going to say, is that my resulting model good or bad? And then produce that downstream. So in terms of how these tools combine together, I see Cloudflow as being a client of something like MLflow, where we take that output that MLflow is creating after doing its training process, and we use this to apply it into a runtime, into a real-time streaming pipeline. Yeah. So I think if you would say the vertical here is MLflow and the horizontal here is Cloudflow, this is how I see them working together.
Okay, great. Well, this was an excellent Q&A session, Gerard. Thank you. I think we really got great answers to everyone's questions. Well, folks, that's all the time we have for today. Gerard, thanks so much for this excellent presentation. And again, we remind everyone to check out cloudflow.io to start there. And you can get in touch with us, you know how, or we'll get in touch with you via email, most likely. You can expect an email of this recording and slides sometime next week, so stay tuned for that. And again, thanks everyone for joining us today. Thanks again, Gerard.
Yeah, that was my pleasure. Thanks for organizing, Oliver.
Oh, you bet. Bye-bye, everyone.